Recently we talked about plotting a graph of a rational function. The rational function that we were considering was the function f of x equals x minus 5 over x plus 5. And we came to the realization that there had to be a vertical asymptote at x equals negative 5, because that causes the denominator to become equal to 0. And that would mean that we were doing division by 0, which is not allowed. So on a graph, we plotted the vertical line x equals negative 5. And we see that that is a vertical asymptote. If we zoom out a little bit, we can see that that is indeed a vertical asymptote. We also considered what happens horizontally, in other words, for a horizontal asymptote. And what we discovered is that we can divide the leading coefficients of the polynomials that are in the numerator and denominator of our rational function, as long as the degree of the polynomials are the same. In this case, the degree of each polynomial is 1. In the numerator, we have x minus 5. Really, we can think of that as being x to the first power minus 5 times x to the 0 power. In the denominator, we have x to the first power plus 5 times x to the 0 power. And keep in mind, x to the 0 power is 1. So 5 times 1 is 5. So the leading coefficient in the numerator is 1. Whenever we don't write a coefficient in front of an x, we understand that that means that the coefficient is actually 1. And likewise, in the denominator, the leading coefficient is 1. And when we divide the leading coefficients, we get the y asymptote. 1 divided by 1 is equal to 1. And so we plotted the line y equals 1 as a horizontal asymptote. The asymptotes you notice in the drawing are dashed. Now, another thing that we considered, though, recently was that if we do polynomial long division with the polynomials that are in the rational function, in other words, if we divide x plus 5 into x minus 5, we end up making the function in a different form, but it's still the same function. And so what I wanted to point out to you was that that function that we end up with, which ended up looking like this, okay, that ended up being the same exact function, which was negative 10 over x plus 1. Okay, and we'll come back to that. Okay, is actually a form of the parent function f of x equals 1 over x, okay, which I plotted on this graph as well. So I'm going to make that disappear for a moment. Now, so in other words, what we can say is that this function, which turned out to be negative 10 over x plus 1, is just a series of transformations of this parent function f of x equals 1 over x. So let's see the series of transformations that we can do to get the same function as x minus 5 over x plus 5. So here we have our parent function f of x equals 1 over x. So the first transformation that we're going to do is we're going to put a minus sign in front of 1 over x. And so look carefully at what that does. Okay, putting a minus sign in front of 1 over x flips the function about the x-axis. So it takes the portion, that is in the first quadrant in the original parent function, and it flips it down to the fourth quadrant. And it takes the part of the function that was in the third quadrant and flips the parent function and flips it up into the second quadrant. So we end up with this graph. Now that was the first of the transformations. Now the next transformation that I want to look at is what happens when we replace the 1 in the numerator of the parent function with 10. And so you should be able to see that excuse me, try that again. Okay, so we're going to put a 0. And what that does is it causes the vertical stretch of the parent function. So it takes all of the y values and shifts them either further upwards or further downwards, depending upon which portion of the graph we're talking about. So for this part that's in the second quadrant, it shifts all of the y values up. For the portion that's in the fourth quadrant, it shifts all of the y values down. Okay, so far, both of those transformations, putting the minus sign in front of the parent function and then multiplying the parent function by 10, those transformations did not change the positions of the asymptotes in our function. The next two transformations will. So in the denominator, we're going to change this to x plus 5. And that actually changed the asymptote. Now you notice that we originally had the asymptotes plotted at x equals 0 and y equals 0. So now I'm going to use this slider to slide the vertical asymptote over to -5. And if we zoom out, you can see that that is indeed our vertical asymptote. So we have a vertical asymptote at x equals -5. So another way of looking at this is that adding 5 to x in the denominator shifts the entire graph of the parent function to the left by 5 units. So next we're going to consider what happens if we make the transformation of adding 1. Okay, now that also had an effect on the function. What it did was it shifted the entire function up 1 unit. And so let's see what happens when we shift the horizontal asymptote as well. We're going to move it over until we get to 1. And then if we zoom out, we see that that is indeed the horizontal asymptote. Okay, so this polynomial function, by doing polynomial long division, we see that it is essentially just a series of transformations of the original parent function 1 over x. So let's compare this graph to the graph that we had originally. So here's the graph that we had originally, which was for the function x minus 5 divided by x plus 5. And here we can see that we have a horizontal asymptote at y equals 1, and we have a vertical asymptote at x equals -5. And then notice some of the points that this seems to pass through. This seems to go through the point. Let's go over to this one, -15, comma 2. Right, so if we go back to the function in the other form and we zoom into where our original function was, this also passes through -15 too. If you compare other points, like this point over here, which is at 5, 0, our original function, you see it also goes through the point 5, 0. You can see that these two graphs are exactly the same. So polynomial long division leads us to a form where we see it is just a series of transformations of the original parent function, which was f of x equals 1 over x.